Assalamu alaikum sir. Today we will be presenting our project titled as Speed Control of DC Motor using PWM. My name is Nasib Jaman and my ID is 2106060 and my partner's name is MD Nazmul Sakib and ID is 2106061. The objective of this project was to control the speed and the direction of a DC motor by varying the duty cycle of a pulse width modulation signal using operational amplifier as the primary circuit implement. So basically the objective and the primary statement of our project is we are aimed to control the speed of a DC motor by adjusting the duty cycle while maintaining a constant frequency. We also want to reverse the direction of the motor and we will be using only OpAmp to design the whole circuit and some resistor and capacitors. So basically, what is PWM signal? The PWM or the pulse width modulation signal is a technique where the variable white pulses represent the amplitude of an analog input signal. By changing the duty cycle, we can control the average voltage delivered to the motor and so its speed. Basically, we can use these techniques into robotics, conveyor system, and fans. So now let's jump into our design component. Our design consists of the following key components. Sawtooth oscillator circuit generates a sawtooth waveform. Also, they control the frequency and the reference voltage via potentiometers. And to reversing the direction of the motor, we will using an SPDT switch. Basically, our circuit components are op-amp, resistors, potentiometer, capacitors, and diodes. Here is our full circuit design. Basically, the circuit starts from the left of the pages with creating a square pulse which is passed through an integrator circuit to produce a linearly changing voltage. The resulting waveform that rises gradually and falls sharply and which is the characteristics of a sawtooth wave. The resistor in the circuit are selected to regulate the current flow during the rise and the fall intervals. When the waveform is rising, the current flow through one specific path with a control resistance value ensuring the steady and the gradual increase. On the other hand, during the falling interval, the diode switches the path, allowing a much faster current flow. These abrupt changes creates a steep drop in the waveform. Op-amp number 3 basically offsetting the output from the op-amp number 2, which will ensure that the sawtooth waveform will starting from the origin.
Assalamu alaikum, sir. My name is Mohammad Nazmul Sakib. My ID is 2106061. Now I will discuss about all the rest of the part of our projects. Now, the first part is the sawtooth oscillator, and we are using op-amp only to make the sawtooth wave. Here, there are three op-amps, and in the left two op-amp we use for the oscillator, especially the sawtooth waveform. And to make the waveform to a certain level and to a offset, we use another op-amp, the three op-amp. Here we use the formula for making the triangular wave, and we manipulate them by using two diodes to change the V rise and V fall time accordingly. This is the formula of the frequency of our sawtooth wave. We choose the R3 and R4 accordingly so that the rising time will be so large than the falling time, and it will mix the sawtooth waveform. Here in the comparator part, we use two signal to as input. One is a sawtooth that we made using the three op amp, and another one is from the pod, which use as a reference voltage that helps us to modulate the pulse width, and that's how we can make the pulse width modulation. And as we are not only making the pulse width modulation, also the switching direction of the DC motor, that is why we are using another op amp to make the minus P pulse so that we can use them in the power supply unit. Um, Here it is a power supply, and in another one is the SPDT switch. Here we are using the minus B pulse, the plus B pulse to switch the direction of the DC motor as well as that controlling the speed using the voltage. Now this is our simulation outcome in PSpice. Now I will discuss about our actual PSpice file and also the Proteus file. Here it is our circuit, and here we already talk about the three op amp which are used for the sawtooth waveform. Here in the top right part of this circuit, we are placing the voltage source, and here in the bottom right portion, we are using the SPDT switch. And here in the comparator, you can see that. Now we are going to run this um, file and simulate what will happen in the PSpice. Here, after 25 millisecond, we are changing the direction of our switch so that pulse width modulation once is from 0 to our certain voltage, that is about here, about we can see that is about 13 volts, and another 25 millisecond to 50 millisecond that reverse, so the direction of the motor will also reverse. Here we can see that the pulse width modulation is about 80% around duty cycle, so that we can get about the 80% of the highest voltage, about 13.4 volt, and we can change them here in the potentiometer. And here we are using 0.8. If we replace this thing as to 0.5, then the duty cycle will be the half. And now after simulation, we can see that we will be able to see that the voltage outcome from our PWM will be the half of the total. And you can see that the duty cycle have turns into the half of the total duty cycle. It's 50 duty cycles, so the voltage will be become half. Here is the transient analysis part. You can see that the same project we have made in Proteus also to demonstrate it more beautifully. Here you can see that there is an OpAmp for the sawtooth waveform. There is an oscillator to see the outcome from the wave, and this is the voltmeter, and the SPDT switch is also here. There's a power source on the right top. Okay, now we will run our code, and you can see that from the oscillator, and it will be more intuitive to see what is going on actually here. Here we can see that at the red color, this is generated from the first op-amp. This is the pulse of square pulse, and then this pulse have been integrated by this op-amp, and then we can create the sawtooth, and then sawtooth will be offsetted by this op-amp. And after that, that this op-amp will be act as a comparator. The sawtooth will be input, and this terminal 2 and the third terminal will be the reference point here. Okay, so you can see that we have put two potentiometer here. We can change the frequency of our PWM here, potentiometer. If we change the potentiometer, we can see that the frequency have changed. Also, if we can decrease the potentiometer, you can decrease the frequency here. So let it at the middle point. So this is our desired frequency, and this potentiometer will help us to change the duty cycle. So I am removing the portion here that doesn't need it, and here you can see that the um, this is our outcome. We will see them later. So you can see that the blue one is our sawtooth, and the green one is the reference voltage. So if we change the reference voltage, and then simultaneously our outcome of the duty cycle will be changed. Now you can see that as we put the reference voltage at the middle point, our reference and the duty cycle is also half. So the reference point here will be the same as the outcome of the voltage, because the average voltage will be the same. If we increase the reference point, also the duty cycle is increasing. Similarly, if we decrease the reference voltage, our pulse width modulation, the duty cycle will also be lessened. And in that way, we can change the pulse width modulated weight of the pulse width modulation PWM signal by using this potentiometer, and by changing the pulse width of the pulse width modulation signal, we can change the voltage. By changing the voltage of the DC motor, we can change the speed of the DC motor, as well as here is another signal that is switch, that is P pulse and P minus B pulse, that can change the polarity of the direction of the rotation of the DC voltage. As the switch are turning on and off as a square wave, so the DC motor will not distinguish between the on and off. The voltage is also lessening. As we increase the reference voltage, the voltage is increasing as the width are increasing of the PWM signal. As a DC motor, it will only count the average voltage. So that is our all about our project, and we try our best to demonstrate it in a very good way. So let's back to our PowerPoint presentations. the simulation outcome from our PSpice and the simulation result. You can see that the 100% duty cycle will give us the 100% average voltage, and the 50% will give us the 50% voltage. Here are some limitation. Request dual power sources. You can see that all the op amps are using two dual power, not one power. PWM control is not optimized for non-motor DC component, non-linear motor component. And also we want to make PCB for, we already make it Proteus, so we can make PCB easily, and that can be used to make as a practical implementation. We will try to include driver components for universal compatibilities and add low pass to stabilize average DC voltage, and we want to explore the triangular and trapezoid signals. So the PWM controller circuit effectively controls the speed of a 12-volt DC motor using op amps. Real-life implementation and PCB designs would address limitation and improve performance. We'll try to do that in future. These are the reference from where we took the information and all the resource. That's all from me. Thank you very much for your kind attention to our video.